In this video, I'm going to generalize the Newton's second law in rotational motion. What do I mean by generalize? You remember when you ask somebody what's the Newton's second law in linear motion, for example, they say F equals ma. When in rotational motion, they may say torque is equal to I alpha. Yes, they are right, but these are the very primitive versions. The generalized is not like that. In linear motion, force is equal to rate of change of momentum in every second, delta P over delta T. This is the generalized format. And so let's substitute the force for its brother, the torque, and let's substitute the momentum for its brother, that's angular momentum. So it's better now. Torque is equal to rate of change of angular momentum in every second. This is the generalized format. So let's have more detail. Momentum can be broken into its components, mass times velocity, okay? And also L, the angular momentum, is broken into I and omega. I, is brother of mass, moment of inertia, and omega is the brother of velocity, this angular velocity. So let's write it tau equals delta I omega over delta t. Okay, go back to the left. Here we have force equals, okay, let's say first mass is constant. So it's going to be mass times delta V over delta T. Then let's say velocity is constant, V times delta M over delta T. This is the generalized format. Likewise, we can do it for the torque. If I is constant, it's going to be I times delta omega over delta t, and if omega is constant, it's going to be omega times delta I over delta t. This is the very generalized format of the Newton's second law in rotational motion. But what do I mean by that? Let's say in a case I is constant, omega is changing, like a disk. Let's say this is a flywheel. A disk is connected to an electric motor, and this motor accelerating the disk, okay? Disk has a constant I. I is not changing. Moment of inertia for this disk as mass and distribution of mass is the same always. I is constant, okay? So we don't have delta I over delta t. The second term is gone. So torque is going to be I times delta omega over delta t. What is torque? This is the external torque, okay? So we need an external torque, or let's say in short, a torque, for change the angular velocity of an object that has a constant moment of inertia. So when moment of inertia is constant, torque is needed to increase or decrease the omega. On the other hand, we can have another example. Let's say we have the same disk, it's horizontal, it's connected to the same motor, and the motor is automatically connected to a system to keep the omega constant. Okay, it can keep the omega constant. But let's increase the mass of the disk. Here we have a pouring mass at a constant rate. Let's say this is a pouring sand. The sand is accumulated on the top of the disk, and the mass of the disk is increasing and increasing. So I is changing, increasing in this case. But the motor tries to keep the omega constant, so it has to apply a torque. Here, as the omega is constant, we don't have any delta omega over delta t, so the first term is gone. Torque is going to be omega times delta I over delta t. But why do we need a torque? The torque is required to maintain a constant angular velocity for an object that has changing moment of inertia. Now we have an example. Sand is poured at a rate of 8 grams per second onto a spinning disk. Here I have a spinning disk, and sand is poured at a constant rate, 8 grams per second. So delta M over delta T, rate of change of mass, is 8 times 10 to negative 3 kilogram per second. This is in SI. Okay, the sand lands with a negligible vertical speed at an average distance of 10 centimeter from the center of the disk. So after a while, the sand will make a ring pattern on top of the disk, okay? The moment of inertia of the disk, this is for the disk, is given in SI, 0.04 kilogram meter square, and its initial angular velocity is 5 radians per second. Okay, so at the beginning, omega, its omega initial, is 5 radians per second. No external torque acts on the system. consisting of a disk and sand. When they say no external torque is acted, means that if I write torque is equal to I delta omega over delta t plus omega delta I over delta t, as I mentioned, tau is the external torque. This is 0. Okay? Part A. Calculate the rate of change of the moment of inertia of the system. Rate of change of moment of inertia means delta I over delta t. I'm looking for delta I over delta t. Okay. Guys, delta I over t is actually delta mr squared over delta t. Why? I told you the pouring sand will make a ring pattern on the disk. So this ring is like a point mass. Moment of inertia of a ring is mass times r squared. R is the radius of the ring, okay? But the thing is, this mass is not constant. It is increasing. This is why we keep it in the delta, but as r is constant, r can be out of the delta. So let's write it as r squared over times delta m over delta t. We don't have anything to do with the moment of inertia of the disk. Disk has a constant, original disk has a constant I. This change of moment of inertia is just because of the pouring sand. So here we can just plug in the values. R is 10 centimeter, is going to be 10 times 10 to negative 2 meter. And as you remember, delta m over delta t was 8 gram per second, but it's going to be 8 times 10 to negative 3 kilogram per second in SI. So let's plug in the values in SI. Okay, this is the radius to the power of 2, and this is the delta m over delta t. The answer is going to be 8 times 10 to negative 5 kilogram meter square per second. Rate of change of moment of inertia. And the reason is just the pouring mass. Part B. Calculate the initial angular acceleration of the spinning disk. Initial angular acceleration, alpha. Let's go back to the Newton's second law. Tau is equal to I delta omega over delta t plus omega delta I over delta t. Question says there is no external torque acting on the system, so we can remove the torque. It's 0. Now I can write it as I delta omega over delta t is equal to negative omega delta I over delta t. Just keep in mind that my goal is delta omega over delta t, that's alpha. So let's write it as alpha equals negative omega over I delta I over delta t. Delta I over delta t is something that we already found. But omega and I are initial omega and initial I. Okay, because this is initial acceleration. Initial omega is given as 5 radian per second, and initial I is the I of the disk. It's given as 0.04. So let's plug in the values. And here I have the I found it in previous part. 8 times 10 to negative 5 in SI. So the answer is negative 0.01. Why the answer is negative? Because basically it's decelerating, you know. And so we should have a negative sign indicating that. Part C, explain whether the acceleration will remain constant as the sand is being poured. You remember, I found that, okay, alpha is this. It's initial alpha, 0.01. But is it going to be changing or constant, decreasing, increasing? It's very important. You remember, alpha was absolute value of that. Okay, forget about negative sign. Is omega over I, delta I over delta t. Sand is poured at a constant rate, so it is constant, you know. But as the sand is poured on the disk, the mass of the disk is increasing, so I will increase. On the other hand, increase in I, you know, will decrease the omega. Okay, so on the right side, upstairs is decreasing, downstairs is increasing, so both have decreasing effect on the right side. Likewise, the left side also will decrease. So alpha, as the time goes on, will be less and less. Okay, we are done in this video. Thank you very much. Take care. See you soon.